All right. Shika, are you ready?
Yes. Can everyone hear me and see my screen?
Yeah.
Yeah. Okay. Let's get started. So today the paper I'm present is the scalable gradients of the stochastic differential equation, and I think it's published at the AISTAT last year. Sorry, 2000, the year before last year. And I think the authors group, they're from the NeuralODE group, like the Ricky Chen and David. They're also the author of the NeuralODE. And I think its paper is have their a great influence because it's just published less than 2 years, but have them more than 100 citations. So let's get started. And so the content today, to fully understand this paper, we have recap some definition about the SDE, and even with the NeuralODE and joint method. I think some of you may be familiar with the SDE, especially for the NeuralODE and joint, but some of you may not. So I will spend some time to go through the key points of such work, and we will go through the co-contribution about these papers and to understand it fully. First, we talk about the SDE. So what is the SDE? SDE is just a generalized ODE, but add some randomness terms. So what exactly the randomness term is called the Brown motion or called the white noise. For here, the formula I show you here is the integration for about the SDE. However, its differential for is something like this. I will write here for the dzt differential respect to t and equal to our function, maybe it's zt t, and multiply the sigma zt t and wt. The W here is the white noise, and the big WT is the Brown motion. So what is white noise? Actually, you can consider at each time points, if we have the random Gaussian, we have the random sample from a zero mean Gaussian. And remember, at each time step, we have these random things, and make this all the time step become continuous. And the things is called the Brown motion. And the B and the C here, the B here is called the drift term. It's a function about the hidden state or the hidden function, and also a function about T itself. It will only focus these parts. It's just the ODE. And when we add these parts, it's become SDE. And the theta here, you can consider it as the function or the coefficient about these random terms. And here is the differential term about the SDE, and here is the integration term about the SDE. And I think the tricky thing for the SDE is these parts. And its name is called Eaton integration. Remember, the theta here is just a function. However, the WT here is the white noise being a random sample from a zero mean Gaussian. And for each small step of this WT, I mean the Brown motion, just consider you randomly sample a value from a Gaussian. There could be the possibility you sample a very maybe here very high value about the random about numbers, but with very small probabilities. With high probability, our sample will focus on its errors. However, we cannot ignore the probability we get a very high value from this zero mean Gaussian. And that's the reason we cannot treat these parts, the Eaton integrator, as a Euro integration we handle usually. And I will give more detail about the comparison about the Eaton integration and the Lebesgue integration in the following slides. But right now, I want to make attention. Here is the key points between the differential SDE and your ODE. And we go step to the here. So what's the difference about the Eaton integration and the Lebesgue integration we handle? Here's a definition about these two integration. I think for the Lebesgue integration, we just consider maybe the T0 to T1, and we do a separation on this time interval. And for each step, we just get the function about each small interval and the gap about this function and we do this. And the key integration is the GT. I mean the function we do the partition. Here is the bounded, so we can do the summation directly. However, for the Eaton integration, the partition is a WT. I mean just a Brown motion I've mentioned. Here's not a bounded variation, just like I'm saying. Here is a sample from a Gaussian, and in a Gaussian, you have a very low probability, but not zero probability to get a very high value about the samples. So this thing is not bounded. And that's the reason we cannot obey the usual integration rules, like the partition integration rules. However, we can just do this to the Lebesgue distribution. And WT is not a bounded variation. Is the, I think, the main reason make the Eaton integration very difficult and very different compared to the traditional Lebesgue integration.
Okay. Lebesgue should be defined based on some measure. Is your T here some kind of measure?
Yes.
Okay, then your Ti plus 1 should index a interval, right? There should be some set in the border set.
Yes, but I don't use the terms in the in the advanced probability like the Lebesgue, like the Born set or something, because I think use such terms to describe the system will make people not familiar very confused. But here I just give very intuitive introductions. Yeah, but you're right. I mean the G here actually is a measure function. He measure the is a infinite measures. So the GT's value itself should be never be a finite, should always be the finite things, but not be a finite thing or a bounded value. The GT itself is a bounded functions. However, for WT here, it's not a bounded function. It could be a infinite measure. So we cannot treat it as a usual integration.
Okay.
Yeah. And then
I have a question about so bounded variation means the WT is bounded or not bounded, or the DWT is not bounded.
Actually, I think it's DWT is not bounded.
Okay. Yeah, makes sense. Thanks.
Yeah, because DWT just means the incremental between maybe WT maybe multiply epsilon are very slab, and DWT just gap between these two.
Yeah, makes sense. Thank you.
Yeah. And then given SDE like this, and what's the solution of the SDE looks like? Because it have the randomness in the SDE. So his solution is not never an exact function or something, but it's have the randomness. There are kinds of the solution of the SDE. Maybe for some SDE, the first kind of the solution called the path of the solution. Remember the WT is there the random samples from some Gaussian. If we just draw the random sample WT and store them, then the SDE become a deterministic. We can do the similar things with the ODE. So it will resample a specific path of the WT, the random sample, and then we can use this random sample, the given random sample, to draw a path about the SDE, just like we do on the ODE. So it's called the random path of the solution. And if you can do this with the Monte Carlo simulation, just draw many times of the WT and draw the path. And with these paths or random samples, we can use some something like the particle filtering and smoothing method to do the things. So, and actually this paper, I mean, the paper we're talking about today, the gradients, they are focused on these things, the path of solution. This solution, the gradient, they are based on their path, the path of they draw from the random WT. And another view to handle the SDE to give a solution is focused on the distribution of the solution. Because given many of the WT you sampled from a Brown motion or white noise, so what's the distribution of the state WT? And here is some methods given here, but actually I don't know much about this, and we are not talking about this today. And there's the third kind of the solution is, I think here is a special case about the second. So maybe the distribution of the solution is hard to describe. Can we just model the moments of the XT? I mean, there's SDE solutions, like how is mean become and how is variance become. I talk about this case, I think, last term in my present in the group seminar. Actually, we can use some Kalman filtering with some Gaussian assumptions to model the moments of the SDE. But these things I talk about, I think, and we actually used it to our ICML paper submissions. But today, our focus will not focus on this part, but we will focus on this part, how to get a gradient on the path of the solution. But here is I think the general description, and here I will give some exact example how the SD solution about SDE looks like. Here we just get the first example I will show you is an SDE like here. Remember the X here is the function, the hidden state we want to model, and the lambda is just a constant. So here is the drift parts. It's just a constant coefficient multiply X itself, and the diffusion parts we have no the nonlinear parts, but just the Brown motion with no coefficients, and it's very simple SDE. So his solution will look like something like this terms. Remember, this term is a diffusion terms. Can be get exactly, and this term is the eta integrator we have talked about previously. Actually, we cannot handle this thing directly, but we can draw the WT and give a pass. Draw a sample from this WT and draw a pass about this term, use some numerical pass, and then we can you can see here the red lines here in the figures, just corresponding to their different samples from the different DWT, and we draw this function, follow these formulas, and here's what we got.
How do they draw a path of Brownian motion?
Actually, just consider maybe here's their time T1, 0 T1, right? And at each step, actually we have to describe this their continuous things. We draw our Brown motion. I mean their random Gaussian, maybe here, and then we just plug in the sample you draw at each time step, just more time step, and plug it into this integration form, and with a numerical method, and you can get the one pass.
So I mean, let me think about that. So I mean that if you want to integrate from T0 to T1, you first discretize this interval by a small interval, right?
Yes.
Small space, and then for each space, you're gonna generate a standard Gaussian random variable, or standard Gaussian random variable with variance being the length of the small interval.
Yes, I think your second thing is right. Actually, when I just want to draw a sample from some Gaussian, the Gaussian is mean is 0, and its variance is related to the length.
It's delta, like
it's called the density of this Gaussian.
And then with the plugin, how do you plug in? Just sum up of the.
Yes, just a simple sum up.
Okay.
Yeah. And here I think is for this example, and here is the solution about this very simple SDE. Another example is
this a so-called random Runge-Kutta? I don't know if I know there's some numerical solver for SDE.
I think the Runge-Kutta should be some second order trick. I think it should be more complicated than this. But they're like the SDE integration or SDE solver. Most of these are based on the sample you draw from the random, and then when plugging into is to compute this integration, they have different methods, like the Runge-Kutta you are talking about, maybe the ORAR or something, which is very similar to the ODE integration solver.
Okay.
Yeah. And here I just show you the path about the solution of the SDE. And another example I want to show you, which is about the moment about the SDE. For here, we start from this. This is the second order stochastic spring models. On the left-hand side, is some second order derivative, one order derivative, and some given functions. And W here, of course, is still a random noise. And with some variable transformation, we can build this two-order integration to a vector-wise one-order SDE. So trait is actually, I think the formation here is let x1 equal to x2 equal to the dxct. When you use this variable transformation, you can from these two-order things to a vector-wise one-order SDE. And very similar to the previous example, this one-order SDE have the constant drift and diffusion terms, which is relatively simple. And then use some variation, you will get the solution. Looks like these things, but I don't list here. And then the tricky thing is I can take the expectation on the solution on these parts, and with some assumption and some property about the atom integration. Finally, you will find the first moment, I mean the mean, and the second moments, I mean the variance about this solution itself can be written on these terms. A new SDE, a new ODE system. Here is the mean about x1 and x2. It's just here's the ODE, and here is the covariance matrix about x1 and x2, and it's also a ODE. So just another kind of solution about the SDE. But if the F and L are constant, then the mean, the first and second moments of the hidden state of function itself follow another dynamic system, to ODE. But however, it looks very nice. However, here the F and L is a constant function. If it's not constant or nonlinear, things get very hard, and I think it's very hard to get such a beautiful for like they're using a new dynamic system to describe its moments. But however, some work like their particle filter and some smoothing method, they are doing the similar. They want to do something like this. I do some assumption on the nonlinear term, and finally I want to describe the solution. The moment of their solution, use their new numerical systems, dynamic systems. But actually here, I just want to show you there has these things, but not here is not their key points of our present today. And then we go to recap their newer ODE and their adjoint methods. Let's switch to some script derivation to make you better understand this. So what is the neural ODE? Can everyone still see my screen right now?
Yeah.
Yeah, great. Let me use these colors. So here is a 4 about the neural ODE. The neural ODE is still an ODE, of course. The edge function is something is a hidden function we are interested in. And this dynamic system is a function. And the function itself, we can model this function as a neural network. The neural network takes the edge hidden state as the input, of course, and T as the input. And the theta, is the parameter about this function. Sorry, we just focus on very simple case. Sorry, 1 second. I think there's some noise here. I will use my earphone.
There are some echoes.
Yeah, because I'm in the office and I think Shibo, his computer is playing out my voice. Everyone hear me right now?
Okay, better now.
Yeah. And we just focus on a very simple case. Just we start from some given ht1 and with this involving with this dynamics, and we get ht1. I mean here start here, and here's end 10 points. And at the end points, we have some observation about this function, about the data set. Here's the real samples. And if the neural network or called theta is given, I mean, here the things in the pink box is deterministic. We can still use some numerical solvers to get the HT with these terms. So here is the NN, I mean, the theta here is given. So I think, right, as far as any questions? Yeah, great. So just like I'm saying, when we just focus on the one step involving from the HT0 to HT1, and finally we'll get some observation. And we use this observation, we can build some loss function. Because the theta here, I mean, should be some bad theta, but actually, we want to just compute or optimize the theta to make the involving from the HT0 to HT1 to be exactly match our data, to match our observed values. So our goal, so how to optimize the theta in F. So of course, the answer is gradient. So our final goal to this case, we want to compute the gradient respect to the theta about the systems. So how exactly compute this, I think is the key point of the neural ODE. Actually here, there are lots of the transitional methods to compute this. But remember, these things, the formula 0, the integration, because it's a numerical method, these formulas, these parts, is total non-differentiable. You cannot just call some numerical solver to compute the HT1 and then call the autodiff. You cannot do this because these parts, these integration parts, is non-differentiable. So how we exactly compute this? There are some other methods like the sensitivity analysis, but the traditional method, it has a very expensive on the memory cost. So the method we are focused today called the joint methods. And this method is to compute these terms, but with efficiently memory cost. And what's the key idea about a joint method? I want to go to very deep in there how we derive from the scratch to get a joint, but to let you know the key points. The key point is we define some new variable called the joint state, like I denote as AT, and is equal to the gradient about the loss function and respect to their hidden state, I mean the function itself, HT. And when we define these the joint state variables, and after some very complex derivation, we'll get some very beautiful form. The beautiful form is something like this. The AT, gradient of the AT itself, respect to the T, is equal to the AT, and multiply the F, the gradient of F, respect to the H. Remember, F is a function like a neural network, and his input is HT. So this term, the term in the orange box, this term, he always have the analytical form, or you can just compute this with the autodiff function. Just consider F is a neural network and H is its input. Of course, we can call the autodiff in their PyTorch or TensorFlow to get these terms. And AT is something we want to near high. And the Formula 1 itself is become a new ODE system. And every term in this system, in Formula 1, we already know this. We can solve this by some numerical method to get the AT. And there's the boundary is at the AT1, I mean the endpoint, because at AT1, we all know the HT1 and to compute the loss. So the boundary term here, this term is null. So we have the boundary conditions. We have the everything know the system. We can, of course, we can call the numerical things to get every times to get the AT. And when we get the AT, so what's and especially the AT0 is the start initial state about these things. So what's the next? When we got this AT from the formula 1, we do the similar things, define the adjoint state for theta we're interested, and even the t itself. But actually, in our work, we are not focused on this term, but focus on this term. We just define the a theta t like the gradient of the loss function with respect to the theta. I mean, maybe the parameter of the neural network. And remember, here is our goal. I want to compute this and to update the gradients. And how we exactly get these terms is still with some duration. We'll find the AT, the a theta t, I mean, gradient of this respect to the t is equal to a formula like this. The AT and the parameters, the gradient of the f respect to the theta. Recall, f is a neural network, is some given system. And if the theta is given, this term could be either an analytic for, or we can compute this term with some autodiff. And AT is the terms we just compute from some from these systems with some numerical solvers. So again, everything in this new ODE system, I mean the formula 3 is null. The AT itself is null from the, and here is from the autodiff. And then we can call the numerical solver to solve this ODE again, and we will get the a theta t. I mean the gradient of the loss function at the actual time step we want to. So actually, we have finished all the things we have got, and recall the process. The general step for the joint method. At first, we solve the formula 0 to get HT. The formula 0, I think here is the initial function, initial ODE, and with some non-optimized theta, we can get a HT. And then we go to the another second ODE. I mean the ODE about AT itself. I mean it's a system right here, right? It's the second ODE, and with solving this ODE, we can get the value about the AT at the arbitrary step. Is the second ODE we're solving, and then we just solve the third ODE system. The third ODE system is right here. When we got HT, when we get AT from the first two ODE system, we can compute this one and use some numerical solver, and finally we'll get the gradients. The final goal we want to use. So I think it's a general step about the joint method, and with these 3 steps, you don't have to story everything. Actually, the memory cost for this, I think, is big O1. You just keep doing forward, and you finally will get a gradient of the loss function with respect to the theta, and then you can use this gradient to optimize your theta. So it's clear and makes sense for everyone. Yeah, great. So, and we'll go back to the slides, but remember here, the joint method is just our memory cost method to compute the gradient about the theta. And the general step is to solve 3 ODE, and the very key point is to introduce the AT itself. And with this very clear, and you see this illustration will be very clear. Here is here. I mean the upper parts is just show the general step we do the integration for the initial SDE, and the joint state is we introduce the AT, and we just go to the backward integration from the endpoints and get AT in every step, and with the AT we can compute the back forward get a gradient of the theta we're interested in. So actually, when we first compute the forward integration, and then for the joint state, we do the backward integration, and we can compute the gradients. And in the neural ODE system, remember the forward integration and the backward integration. They're the same things, but just change the order about their integration. Maybe for the forward, it's from the T0 to T1, and for the backward, it's just for the T0 to T1 to T0. So, and everything here, I think is the same, but I just change the order here. So it's trivial, right? And you will see the difference when things go to the SDE. I mean, the forward integration and backward integration. And I think here is a slide to highlight the advantage about the joint methods with the neural ODE. So this paper neural ODE is the first combine of joint method with the reverse mode autodiff. Just remember the duration we just went through. There are some terms we have to call the autodiff in the PyTorch TensorFlow to compute. And when do the backward integration, these parts. Here AT is a vector, and here is Jacobian integration. And in their numerical solver, they optimize. They can have some speed advantage because they compute this vector Jacobian product together in the numerical solvers, and they can get a very quick speed. And here
what's X0 here?
X0, I think here just from, I mean, the initial state about their, here's the gradient about their initial states, right?
What's their initial state?
The initial value about their ODE system.
I think it's H in Shikai script.
That's this one.
So yeah, is this still the neural ODE thing?
Yeah, it's still a neural ODE thing. Remember, when we set a neural ODE, we have several things to optimize. The first is the neural network is parameter. I mean, called the theta in my derivation. And the second thing we can do the optimize is the initial value about this, right?
Yeah, that's why I think that neural ODE paper introduces a weird way to explain the adjoint method, like to define theta and t and initialization together as one state, right?
Yes.
So that's why I ask you, what's X? What does X mean? X includes all the three elements, like initialization.
No. I think the formula here he show you. I think it's only the gradients. I mean the solution about the initial state, but they omit the gradient solution respect to the theta, because your gradient respect to the initial state to your theta is the same things. But here he just show you the formula of the gradients respect to the theta to the initial states.
Yeah, if it is a gradient with respect to initialization, yeah. In my recollection, I don't think there's an integral here. There's just A0.
Yeah, but you never know A0. A0 is something you want to optimize, right?
A0, when you solve A, you got A0.
Yeah, you have
is the adjoint state, right?
Yes. So you have got A0 through its integration.
Also, I mean, this is a way to more quickly solve this joint ODE, backward joint ODE.
Yes, I mean the formula here, he just used the example about when we compute the gradient respect to the initial states, and he showed the formula here. And he say in this formula, in the integration, when we call some numerical solver to solve this integration, if in the inner terms is the VJP, I mean the vector Jacobian product, you can do some inner optimize to make the make the computation about the neural solver here more cheap and more faster. I think here's the point we want to highlight.
But what?
Z? Z
Sorry?
is H or something. Theta.
Yeah,
So
Z,
theta is your neural network parameter. Z is what?
Z is the hidden state. I mean, sorry, so here I think the notation is a little a little confused. The Z is I think is equal to the H. Is the function we're interested.
Okay, once they implemented so-called vector Jacobian product, how to do the integration? They use Euler method.
I don't know. I think here's the things we don't see, but in the very in the implementations, they just say we see the VJP and the integration, the numerical solver to compute this integration will be very cheap and faster.
I'm asking you because in the paper, in our recent paper with Shibo,
Yeah.
when we solve this adjoint OD backward,
Yeah, it's very slow, right?
no, we also use this same trick
Mm,
because our hidden state is our hidden is very high dimensional, and the Jacobian is very high dimensional. I mean, Jacobian is a huge matrix. So you use that vector Jacobian product. But if you calculate that, I think we have to maintain the intermediate states and then use the Euler method or the second order Euler method to do that. So I'm curious how they implement their solver.
yeah, sorry, actually I don't know.
They use the checkpoint also. I checked the code.
Oh,
They
okay.
they state that they use the checkpoints to avoid the explosion issue. I checked the paper and they state that.
But why do they define a high dimensional state? It's not necessary, right?
Which variable? Which variable is the high dimensional here?
Z. If Z is not high dimensional, it's not necessary to do this.
I think Z is high dimensional here.
If you assume your neural network's output is not or the width of the neural network is not very large, it's unnecessary to apply this trick unless your neural network width is very large. Like what we have done, right? Because we treat the state as the mammals all the parameters. It's very high dimensional. But here for the neural OD, they just want to construct an infinite deep neural network. The state should represent the width of the neural network. Right? If your width is not large, it's not necessary to do that.
But T could be large here. So if your Z or X is not very large, but your T is a long horizon, it could still face the explosion issue.
T is large is okay because if you use your Runge-Kutta or use whatever method, you just need to calculate a few values at T, right? Every time.
Yeah, I'm curious how they define the T here, because T is just a discretized deep layers.
They have to optimize T0 and T1 because it says it's an infinite deep neural network. You have to define the starting time point and ending time point.
Yeah.
They optimize them. But you if you assume like T0 is 0 and T1 is 1. So if you even use Runge-Kutta whatever method, every time you just calculate a few time points, you just linearly combine them together.
Yeah, but I think in their code they define the big T as the number of hidden layers.
Yeah, big T is the number of hidden layers.
Yeah.
Big T is the continuous version of the number of hidden layers.
Yeah. So each
Yeah.
so each hidden layer you can see it as a observation of the ODE system.
No, there's no observation. What they observe is they even don't know the time points. What they observe is just output and big T. They want to optimize with respect to big T, and also the other parameters which determine the time derivative.
I think, I don't know, I'm not very sure about that, but I think they also consider the output of the intermediate layers. No, they don't. No. Sorry about that. No.
Imagine you have a task to do the.
No, you don't have the ground truth of the hidden layers. So
hidden layers. Like suppose you want to construct a model to classify images. If you have some hidden output, like if you have 10 classes, then your hidden outputs should be 10-dimensional, and then you softmax to get the class the label.
Yeah, but yeah, right. But I think that the neural OD model is just used as some feature extraction layers. They have independent input layers and output layers. After those, I think in their code, after the neural OD layer, they also have a CNN or softmax layer or something. So Z here is not 10.
Oh,
it could be 100. Yeah. They have a ResNet. They just use this neural D as the building block of the huge classifier model.
Okay.
Yeah.
Yeah. Can we just move on?
Yeah,
sure. And here we're just talking about the neural ODE and the SDE and the joint. So nature extension is, as we can use the neural network to parameterize the ODE, can we just use the neural network to parameterize the SDE? I mean, the diffusion function, the drift function. Of course, this extension is very easy and trivial. And can we still use the original joint method to optimize this? Actually, this part is non-trivial and very bit difficult. And this part, I think, is the key contribution about these papers, because this point is very easy to work out, and actually lots of people have followed these things and to build this neural SDE. And the difficult part is how to optimize this neural SDE. So here he gives some reason why generalization of the joint method to SDE is very different. So actually, I think the key points which I marked with the red box is, remember in the joint method, we have two steps. The first is integration forward, move forward, and then backward with the joint method, with the joint state AT. However, consider our SDE. In the forward, you just sample some random noise, and actually in the many iterator, there are nodes. There is not very clear what is solving our SDE backward in the reverse directions. And actually, if we still use the eta calculus to define our ODE, our SDE. The backward directions integration is not even well defined. So this is the biggest difference. The difficulties in to apply the other joints on the SDE, because the backward integration is not well defined. So actually, how they handle the backward integration and give it a well-defined and things. And here is a very, I think, very tricky part here. But actually, it's some term which I'm not very clear, but just give you a big ideas. They apply something called the stochastic flow. And they say we use these mathematical tools, you can define the backward solution or integration about SDE. Use these toys. And to use these toys, you cannot use the Eaton integration, but you have to use this they call the Straw-Tarnish for about integration to redefine the from motion on a white noise. And with these settings and use these mathematical tools, you can just define the integration about the SDE in the reverse directions. Here I just give some contents here, but I don't want to to go very deep, because even for myself, I cannot fully understand what is that exactly mean. He used some definitions, I mean, in the advanced random process and even the differential geometries fields to define this stochastic flow. I just pasted the definition here. He just defined here the solution, one of the solution about the SD at time points, and then he just define a collections about his maps from this, and then he just proved some very good property about his called the continuous map, called the differential these terms. I even don't know how to pronounce it, different morphiness. And then we use this definition, and with this term, with this definition, and with these organized ways to organize the integration, you can define the backward SDE in this force. You can see these things, the form about the backward SDE is very similar to the we define a forward SDE. But however, here I cannot fully understand it, so I cannot give you more details. And I think it's not necessary to go to such deep. But they put lots of work in the papers to prove this property, to give why we have to use these tools or something. But the only things maybe we're interested, maybe I think is useful for us, is to use the Straton-Tornius integral to replace the Eaton integral in the.
Shikai, one second. So yeah. What do you mean by time reverse SDE? So you can integrate the same SDE. You can solve the SDE from backward.
Yes.
So
just consider maybe with run T0 to T1, and here is the SDE, right? And we just draw some samples about WT with some neural numerical. We can draw a path about the function from the T0 to T1, right? With the draw sample WT. And however, if we start from the T1, can we recover the path we just sampled? I mean, actually, if we use the integral, we cannot do this. Here, and this backward integrations just called the reverse directions SDE.
So that means the path sampling approach cannot do backward to solve the same FD.
You use the classical definition with the Eaton integral. We cannot recover or reconstruct the path we got from the forward.
Okay, but you mean according to the previous what's the name? It's called
the stochastic flow and this Straton-Tornius for about integration. We can exactly do the backward.
Also, I mean that's just a special family of SDE.
Yes. Yeah,
if SDE has that form, you can integrate from backward.
Yes. Here maybe we start from this one. I mean, let's look at these figures. I think the black line, the true solution is just one path from some draw samples we draw from the forward, and if we will follow the terms of the Eaton integral and to try to reconstruct the path, we'll get the red points dash because it's not exactly match the forward path. However, if we just redefine there is integration parts with its force, the Stratonius force, we can exactly reconstruct the forward path from the addiction from a
I mean,
reverse.
your SDE should be defined based on this stratum reach,
Yes,
bro.
yes. And when we see the definition about the Stratonius integral, I think things is very, very similar. You can in the eta integration, at each small interval, the value we defined on this small interval, we just use the left values. So FTI, Ti minus 1. We just use this left value to define the function value around this small terminal. However, for the Stratonius integral, we use the average about the two ends. I mean, the original value here to define the function value on this small interval. That's the only difference on the definition.
And the limit under the limit symbol, is that pi is actually the space, like the delta?
Yeah, you mean this one?
Yes.
This one just means the partition, like the field is from the T1 from the T0 to T1, and we do split lots of the small interval, and here's partition is called the pi, and the pi what is mean is the number of pi. The number of pi just means the max of the interval, max of the length of the interval. So if the max of the interval is equal to limit 0, so we the limit, it just go back to the integration.
Okay, and it requires that, I mean, the reversible means that, okay, your integral in the SD must be defined based on this integral.
Yes.
Also, it has some form, right?
Yes, we will follow this form to define the SDE, define the randomness pulse. We can do the backward SDE with very clear definition.
Yeah, but it's still restricted some family of the form. It's not for every SDE, even with the Stratonovich integral.
But I'm not sure because they're saying actually if you given a SDE with the Eaton integral definition, you can freely to redefine it with the Stratonius integral. These two forms can be, transferred freely.
You can replace the integral, but what I'm curious is that if you replace all the Eaton integral by this, I don't know who invents this new integral. Is every possible SD reversible?
Yes, I think so. Actually, there are two different definitions of the integrals. Just decided how you do the numerical solvers, right? Because actually, when we use some numerical solver to compute this integration, actually we're computed these formulas, these two different formulas, in some small interval and sum them together. I think it's a general ideal for the numerical solver. And if you use the Eaton integral, it means in the numerical solver, you will compute the value about a small interval. Use this and use the Stratonic lineage integral. You will compute the small interval of the function value. Use this for and then sum them together.
But why the former? Why this Stratonovich integral is reversible? What's the intuition?
I think it's because here is the function value is the average about the two ends. Just consider maybe from here is T1, here's T0, right? And consider we just define the function with the Eaton. The function here is just the FT0 over all the intervals, like here. However, when you do the inverse, use the same Eaton integration, your function should be the FT1 on this small interval, right? So
okay, that's a good point.
Yeah,
okay.
And with average, I think
they want to use the same discretization method to solve. Then yeah.
Yeah. So backward and
you use left end, and then when you do backward, you use right end.
yes, exactly. And
Okay.
with
And
the,
in the Stratonovici integral, you use the middle, so it doesn't change. It doesn't
Yes.
change.
Yeah. And then just use this, and here I think these figures just show you the difference. Use the Eaton reverse and the Stratonic reverse. So use the Stratonic reverse. I mean, the forward and backward pass are exactly same. However, if you use the Eaton reverse, I mean the backward and forward, the difference, because forward use the left end value and the backward use the right end value. That's the difference.
But they still you still need to store every Gaussian random variable.
Yes, that's a very good point. It's another thing you're talking about. Yeah. Actually, you have to store because it's a pass. The pass is determined on the random sample you just draw. So you have to store each random variable here to reconstruct to the back propagation.
I have a question about this. So the forward and backward is depending on a particular realization of WT, right?
Yes, they use the same.
Okay. Yeah, that makes sense.
Yeah, same WT you just draw and you store, and you do the forward and then use the backward. And here is I think the formula about the backward SDE. You have just use the definition we have introduced previously. I think the notation here is look a little weird because it's not exactly the solution about the backward SDE, but it's some stochastic flow or something. But actually, I mean, the general idea is here is the backward SDE, and this time is the Stratonic integration in a backward, and the WT here is called a time river Brown motion, because the forward Brown motion is just maybe the WT multiply the current T, and the backward time reverse the Brown motion is just the current WT multiply the end mode or something.
What does M mean?
Oh, sorry, M.
What does M? I from 1 to M.
Oh, this M means actually maybe you have for here each Brown motion we just consider maybe a 1D Brown motion. However, they are possibly on the multi-dimension Brown motion. So M here is the dimension of the Brown motion.
But I feel if you have a multi-dimensional Brownian motion,
yeah, so you have
to be multi-dimensional as well. Why they do the summation here?
Because actually I don't exactly know why they put their multi-dimension here, but actually in the settings or something, they just set M equal to 1.
Okay, that's fine.
Yeah. And as far as we already have a very clear definition about what backward SDE is, and it's very natural to just apply the joint, because you can use a numerical solver to handle this, just follow the ideal. So
the numerical solver to handle this is simply to discretize the interval S and T, and then sample the Gaussian, then add and sum over.
Yes.
Both?
Yes.
There's not any higher order method?
Actually, in the paper, they don't talking about the the method. I mean, the sum over method they use. I mean, the sum over. I say sum over. I don't mean just do the 1 order sum over. I mean, in the implications, they of course they can do some high order method, but they don't talk about such detail in the paper.
Yeah, because I feel like there still can be some high order. I mean, that just means okay, they are able to generate any point in the path, right? Any point in the Brownian motion path is just a Gaussian variable.
Yeah.
Okay. Yeah. Go ahead.
Yeah, and actually this formula I think is the biggest contribution of the work. They just redefine a backward SDE and with exactly same the form and reconstruct a backward SDE. And with this definition and formulas, I think it's very natural to just extending the formula to the other joint methods. They still define the joint state AT, and then you can show the solution about timing reversed SDE with the other joint is something like this. Remember, we're from T to S, so the integral here from S to T is just the time reverse integration, and the inner points, the inner terms in the blue, they still follow the VJP form, which is consistent with the neural ODE or the joint on ODE. So any problem here?
How they I'm not sure if they derive the adjoint method, does it generally also obey this form?
Yes, actually in the joint, because the forward mode about a joint, the ODE and SDE, they're very similar or exactly same. And the hard point is the backward, because for the backward SDE don't have the well-defined integration. And with these formulas, we already have a well-defined backward integration. And the other parts about the joints is exactly same. But we have here you have two functions. The first is the drift and the diffusion. I think the idea is the same.
Yeah, okay. I intuitively I believe so, but I think it's better to check that because the adjoint method is defined based on the Lagrange augmentation.
Yeah.
And you need to set up you need to set a bunch of coefficients to be 0 to get the adjoint OD. I'm just wondering if they have done such kind of check.
Yes, they did. Actually, I think it's not check, but they just do some proof on the convergence about if we define this as a joint will converge or something. Actually, but I don't go to such detail inside details.
Convergence, what kind of convergence?
The convert, if we just use the definition on the backward SD with this force, where is convergence to the numerical conversion or something.
Okay, yeah, I can. Why I'm asking this? I can tell I'm very upset about their introduction about adjoint method. They kind of hide the key idea of adjoint method. Or in other words, their description of adjoint method is wrong. That's why I'm asking if they switch from ODE to SD, if they do their adjoint method, they should follow exactly what the adjoint is derived and check if this is the right form. I guess they have checked.
Yeah. They have the long appendix on the proof about this formula here. But if you want to see the details, you should search the paper on arXiv. On arXiv, they have the, I think, more than 10 page of the appendix on the proof these things.
Okay.
Is the I here is the number of realizations of the W?
Which term?
The I, the subscript.
Oh, it's possible. I think that's a good guess.
Yeah, I guess that I is the index is I. So I summation over I to M. I think in here they means the I is the number of the realizations.
They kind of got multiple paths.
Yeah.
Oh yeah. You're right. Yeah. Sorry, it could be the map for multiple paths.
They can reduce the variance, I guess.
Yeah. Yeah, thanks for pointing out that. Yeah.
But they should divide it by m, right? If they want to.
Oh. Yeah, I'm not sure. Maybe I should check whether the I means the multiple paths or the multiple dimension about this Brown motion.
Okay.
And here's the comparison about the original ODE of the joint for the new ODE and the SD of the joint. Let me first focus on ODE of joint. The first gives some parameters to optimize start points, stop time, and the final state, and the loss gradient about the loss function gradient respect to the final state and your deterministic. And the first, you call our function called the argument systems. The system will give out the here's the reverse, the dynamics in the reverse directions is multi-z, and here is the directions. I mean, respect to the sorry, how to say that? I think it's something like the loss function respect to the t or something and equal to the at. This is the formula I show you in the derivations. And this function will return these things, and it will be the either dynamics where we'll use when we do the second ODE, the third ODE integration, and kids call the ODE integration to get the gradients. Here is the initial states, and here is the dynamics. We want to do the integration, and the dynamics is given here, given by this function. And here is the start point, here is the end point in the reverse directions. And then we call the ODE integration some solvers to get the gradients respect to the initial state, to respect to the theta. And here is the very high level description about the ODE sensitivities. Just to recall the derivation I just showed you on script. Here is the solving the second ODE or the third ODE. And this function is just the second ODE. Sorry. And use the second ODE, just give some system we have to integrate on the third ODE, and finally we'll get the gradient. And I think the first ODE, they just omit the details to solve the first ODE in the joint methods. And when things go to the SD of joint sensitivities, I mean the algorithm they post, they are exactly the same. The blue text just highlights the actual steps compared to the new ODE. We still need the parameters to optimize and some start and stop time and some final state and the loss gradient. And we have the drift and the diffusion terms and the Wigner process sample WT. I mean the sample you draw from the Wigner process from the white noise. And still the first things are similar. We just got solve the second ODE on the drift function. It's exactly the same. It's exactly the same with the new ODE. And then for diffusion functions, which combine with the random term, defined with the Strautonius integral or something. His argument diffusion is defined something like this. I mean, it's the same thing. You define the reverse. The reverse directions, the reverse dynamics about your random parts, the Stochastic integration, and then give this term and use this second ODE integration, the dynamics. We can do the SD integration to get the gradients. Here is still the initial states. And here, I think it is the dynamics for the drift for the non-random parts, and the sigma hat term is the dynamics of the random terms, and W here is the I mean, is the noise we have, the noise we sample, here is still the integration, the backward integration with up and the start and the start time in reverse. And we can got the state regarding to the parameters. So it makes sense.
Shikai, do they also use neural network to model the diffusion?
That's a good point. Actually, in the algorithm present this score, you can add the theta on the diffusion. However, in their experiments, they don't use their parameters to model the diffusions, but just that is at their constant terms.
Oh, okay. Okay.
Yeah. They claim if we just add some theta here, maybe use a neural network, there are some computational difficulties when we do these things.
You just assume is a variance, some kind of constant variance. They estimate that variance.
Yes, but because actually the experiments, they don't exactly follow the RISC models. There are handled some models called the latent SD. I will talk it very soon. And in such model, the diffusion terms is always are constant or given functions. It's not revoked to any parameters.
Okay.
Yeah. And actually, I want to tell you what I omit of my presentation, but also in the paper. The first is some numerical and convergence proof, just like Shantian just talked about. And another thing, a point I think Shantian just saying is about, because we are handle some paths. The path is drawn from the based on the draw samples from the randomness from the stochastic process, and how we efficiently memorize and index and retrieve such samples. They just propose some tricks or algorithm called the Brown tree to store the random samples of the WT, and to make sure we can store them and retrieve them in the backward. But here I don't go into without detail because I think it's not our interest. It's just some trick or algorithm to efficiently memorize and index. And we'll come to the last piece about this paper. It's called the latent SDE. With what we have introduced, we can use the stochastic adjoint to fit in the SDE. Both set is parameter diffusion and the drift as a neural network. But they claim if we just use the data to use the maximum likelihood to model both everything as a neural network, it will cause a degenerate solution. And his idea is, can we just use some Bayesian latent work? This means to model the SDE, say place the prior and infer the posterior about the parameters, about the process itself. And here is the called the latent SDE. And I will give I think the idea for this is, if we don't use the latent SDE, but just use the neural SDE or something, the hidden states, maybe at T1, we can compute we should assume the hidden state should equal to the observed value exactly. However, with the latent SDE, it's saying the DT, the function of the SDE is some hidden state. We are not able to observe the hidden state of itself, but we have to define some data likelihood. So given the ZT1, I mean the last hidden state, and here's observed value, and we can freely model this conditional port as some data likelihood. And here is the latent SDE. The Z, I mean, just think the value about this function about the solution is not observed based on hidden states, and there's some likelihood between this hidden state and with observed value. Here's the assumption, I think the basic assumption about the latent SDE. But the tricky thing is how to place a prior and inference posterior. Actually, in next slides, these things I think is not very natural to me, but you can just free to post down suggestions. Is the method, is the way they post the prior and the approximate posterior. Actually, the prime or approximate, usually when we're talking about Bayesian, we just put the prime and approximate on some variables, on some weights or something. But here, the prime, the defined, is the process. They put a prime on a process. Remember here's the prime here. And then we define posterior also is the process. And what's the difference about these two processes? They claim, or I think it's not the claim, it's an assumption. They just say for the prime, compared to the prime and the posterior process, for the drift terms, they are different. They are different function. And however, for the diffusion terms, they are exactly the same. I mean, with the same WT and this function of the diffusion term, they are not parameterized, and the function is a constant term. And what we have to do, we want to parameterize, we want to optimize the parameters, both on the prime and approximates. So does that make sense to you?
That's so weird.
Yes, when I first saw this, I think it's very weird, but they do make the definition like this.
So why do they assume the diffusion term is the same?
I think it's you can see this paragraph. I think it's to compute the divergence, the distance between the prime process and the approximate.
That's just for computational convenience, right?
Yeah, I think so. They just says if you have the same function, I mean the same diffusion terms, he says the KR divergence about these two processes, it have the finite values. Actually, they follow some mathematical theory, but I'm not very clear because I even don't know how to define the KR divergence on two processes. But actually, they say with these settings they can do this, and how they exactly compute the KR divergence is based on the sampling path. They just sampled different group about the WT, and then they can compute the KR divergence just based on the path, the sample path. And here I just give you the envelope for the KR divergence. I mean the variation lower bounds. You can see here. Actually, I don't know very exactly why they can formulate out of this, but I think you have to get the key ideal. Key ideal is envelope is based on some samples. You have some observations. Is there observation values at each time step, and you just sample lots of the samples, and then you have to define some functions called the U. So what the U means? U is some functions should satisfy its formulas. The H here, I think, is the diffusion part. Sorry, the notation here is still some strange, but the H here is the prime. Here is the prime drift, and here is the post drift functions.
Oh,
and
so that integral is like a KL divergence.
Yes.
Okay.
Yeah, but actually,
you must have derived the form.
Yeah, I don't know how they compute this U and why they can do this. But here's the form they just give out.
Oh, okay. So that they can use their posterior form to sample Z, the path to Z, and then compute the stochastic gradient.
Yeah. So here N is I think the N groups of the paths about their they just sampled and to compute this.
Yeah, I don't think it's N is a group. Maybe N is just the number of observations.
Oh yeah. Sorry, it's a number of observation. My fault. Sorry. I think the group is something defined on the expectation. I'm not sure.
It's the expectation, right? It's like I have a posterior form. I have a posterior SD actually. And every time I just sample a path from that posterior SD, that I can plug in and calculate the stochastic gradient.
Yeah, I think so. And actually, he gives some more detail the interpreting on the object function. I mean the LO. These terms is called the KR divergence terms. He says if the diffusion is diagonal matrix and non-zero, this thing is just the U here. It's just equal to the difference about the stripped and the sigma here is the given diffusion terms, and then they multiply this and here and treat this as a KR divergence.
Well, what is FP and FQ?
Oh, sorry. So here is just the notation in the last slide, they are different. But here is still the prior drift.
That's H5 subtracted by H theta, right?
Yeah. The P and Q here, I think, is the parameters of the pri and posterior. Yeah. Okay. Here, just the FP, FQ here is just corresponding to the H theta and H phi here. Here is FP and here is FQ. And I think it's consistent with this one. Here is FP and here is FQ. Does that make sense?
One second. Okay. So how do they handle the integral? Like you have to integrate the difference between the two
function. Yeah, of course, it's just a numerical solver, right?
Okay, they do the numerical integration.
Yeah.
Okay.
And you get the loss, and with this loss, just call back the stochastic adjoint to calculate the method, and that is. And I think it's we have finished the main work about this paper and how you construct the backward SDE and construct the stochastic adjoint, and then with these settings we can further construct a latent SDE with this likelihood set, with introducing this likelihood. And the last slide is about another view about this the whole work. He says with the latent SDE settings, the whole models can be treated as the VAE, but with the infinite dimension noise. So what are they talking about? This part is about the posterior, about the SDE. They say they're given some observed values, right? And with some posterior thetas, we can generate some latent variables, latent space variables. It's corresponding to the encoder of the VAE, and the W here is the given draw samples about the Wiener process, and this something is given, and here is the pri process of the corresponding to the decoder. Oh, sorry, it's the decoder about the about things. So finally, he used the SAM.
I see. Okay, this is really
yeah.
Okay, this is really well. You can see that, but I'm still uncomfortable with their posterior approximation because all the randomness comes from the Brownian motion, right?
Yes.
And the Brownian motion is just those standard Gaussian random variables. If you don't decrease the variance of standard Gaussian variables, how do you see that after seeing the data your uncertainty is decreased? More naturally, you should make your diffusion term to be learnable.
Yeah, but I think there are some things they can handle with some computation.
There might be some computational challenges.
Yeah.
Well, of course, if you assume your prior and posterior has the same form, every model can be built as a variational autoencoder.
Yes.
I have a question about the elbow. Can you scroll up a little bit? So
Yeah,
here in the first term, you want to minimize the KL divergence.
Yeah.
But what if the posterior is exactly the same as the prior? The KL divergence is 0.
You mean they are exactly same?
Yeah, because your objective is to maximize the evidence lower bound, and it's equally to minimize KL divergence.
It is possible.
Yeah, I think
Yeah.
It is possible.
in the optimal case,
So if the posterior is the same as the there is another term. Okay.
There's one problem here because they jointly estimate both the prior drift and posterior drift term, theta and phi, right? If you can find the stationary point where theta and phi are equal, and then make the whole elbow to be some local maximum, it is possible.
Yeah.
Maybe you can just make them the same and just maximize the likelihood.
Yeah, it's possible.
Yeah. And I think that's a good point, because there's a point I'm not very clear in that paper. Is because in the general Bayesian inference, we're only interested on the parameter of the posterior, right? However, in this paper, they claim they not only compute the gradient and optimize the parameters on the posterior process, they also optimize the parameters on the prior process. I'm not sure if something like the optimization on the initial state or something, but I don't know why they still want to optimize the terms in the prior.
So sigma here is a hyperparameter.
Where is the sigma?
In the KL divergence term, the sigma is a hyperparameter, right?
You mean this term?
Yeah.
Yes. Here is
so the expectation is taking over the sampled W, and the FP and the FQ are evaluated on the same set of paths. So this looks like the variational inference. You only consider the Euclidean distance of the means. So it's kind of problematic, right? So you're not consider the diffusion term. You only consider the drift term.
Yes, that's I think the weird part. They are talking about SD, the KL divergence. They only compute the difference between the determinists, the drifters.
Yeah, right.
Yeah. And finally, if everything's clear, we go to the experiment parts. So they put two kinds of experiments. The first is on the synthetic data. I think they just what called the stochastic Lorentz attractors. And here is the training data. They have the two modes about the Lorentz attractors. And after the training, they got the prior and some posterior. And here they just draw some samples from the learned prior. Because the prior, of course, this can construct the mode about this training data. And for the posterior, they have a posterior distributions. And when they draw samples from the posterior process, it's in some path is corresponding to the very similar to the training data. And for these figures, I'm not sure what they're talking about. The latent dimensions is something like they draw the samples in the VAE hidden layers and drawing things, but I'm not sure what it exactly mean. But from the posterior sample and the prior samples, they do learn something to cover the Lorentz Lorentz attractor systems. And here is on the synthetic data, and here they also use some real application data. But here to just say use the neural SDE to get the smallest the reconstruction MSE compared to the neural ODE and the other VAE based methods.
What's the latent OD? The reference time.
I don't know.
What it looks like a neural OD here failed.
Yeah.
Yeah, can you take a look at the latent OD? Maybe we have came across it before.
Yeah, let me see. Oh, sorry. I should go back to the paper. The latent OD, right?
Oh, well, the 72.
Yeah. Oh, here's the neural OD, and let's check what's the latent OD.
72.
Yeah.
Okay.
Here, paper.
They're irregular sometimes here. So I thought that is just apply neural OD for RN model.
Yeah, maybe.
Okay.
Go back to this. And there is a summary. Summary is, I think I just copy it from their author slides. And he says the main contribution is he just give a generalization about the joint sensitivities to the SDE. And with the correct definition and we can remain advantage about a joint with very low storage, the memory cost. And then he uses joint to train the latent SDE with such settings and give some very good results. And the next step they want to do, I think, is can answer some of your questions or concerns. The first, they want to say where data models. Oh, sorry, they don't say that things here, but I think in other slides of the present, he say they want to add the diffusion terms as the parameterized also, and here is the paper. Maybe I want to talk next term. Is to just build a Bayesian neural network combined with the SDE, and I think this paper just they put it on archive 1 month ago. So if you are interested, we can go through with this topic and to see how they combine the Bayesian neural network with the SDE.
What do you mean? You mean they use Bayesian neural network to model the drift and the?
No, they just use the network just called the BNN SDE. They just use the SDE to model the weights in a Bayesian neural network. It sounds like this.
Okay.
Yeah, and they already worked it out and put it on the archive, I think 1 month ago.
Okay.
And if you are interested, I can go look at this paper and talk it in the next seminars. And
okay,
I think,
that's interesting.
Yeah, and I think that's it. That's all for my presentation today. Thank you so much.
Okay, just a quick presentation. I thought you're gonna present something in the afternoon as well.
No, because I think actually some of my thought is because I think this group, I mean the Ricky Chen and the Toronto University group, they have follow this topic to work out lots of the paper. And I think the style of the paper is very give lots of the proof and to work out some demos. I don't think so. If we want to plug in some SDE work in our research, it's not such easy. I think it's not don't make me very confident or comfortable. I mean, if we want to plug in some SDE work in our work, I think I prefer the sites like from the Auto University side. I mean this sites.
Oh, the Feynman.
Yeah, either the common filtering or focus on these parts with the moments, with the distribution about SDE, and with some Bayesian Gaussian approximation, and to apply to the tensor work or something. And I think in this work, they just focus on this part of the solution with some very solid mathematical settings and give some new definitions. So I'm not sure. And if for this part, I cannot go to very deep because I don't know some very definitions, some knowledge about the advanced SDE with some differential geography or something. Yeah, so for the SDE part application in our research, I prefer to look more in these parts.
I think for the latent SDE model, they are trying to like move the focus of their work to the distribution of the solution, because they take the expectation of the of their original formulation to get a new model.
Yeah, I think so. Actually, in that latent SDE, they model the XT, I mean the hidden state, not like a distribution, but a process. So because distribution have these moments, right? At each time step have these moments, just like the example I given here. So the solution of our SDE have this mean and variance, and mean and variance have this all dynamic system to involve. However, in the latent SDE, the X is the process. They just model the process and parameters about this X. I think it's kind of similar, but it's not exactly the same.
What's the major motivation of using SDE?
They're talking about their lots of applications have their randomness, and with this randomness, with the SDE, we can do better. Like the
that's because naturally the neural OD itself is not a Bayesian model, is not a probabilistic model.
Yeah.
If we want to give some capability of uncertain estimation, SDE is one way, but more direct way will be, okay, why not we assign the prior over the weights in the neural OD?
Yeah, there are some paper like calling the Bayesian neural OD or something. I'm not sure they're doing. Maybe they're doing the same.
Because that's interesting here. Like previously, Shibo has tried assigning some prior over the neural net over the weights in the neural OD and do the posterior inference, and it looks like it doesn't work very well.
Yeah.
And then we came across some paper who claims that they use HMC to do that kind of sampling in the neural OD. It works well. There's a one NeuroNIPS workshop paper. I guess it's in last year.
Yeah. Okay.
And that makes me wonder why, if you just assign prior over the weights in the neural ODE, you can do well calibration of the uncertainty. Why do they bother to leverage such a complex approach?
I don't know. Maybe they want to give some theoretical contribution because they're just define more mathematical things. Yeah, I don't know.
Those mathematics are very shallow for those computational physics guys. If they learn SDE, they learn the theory. They just copy and paste.
Yeah, but
the literature.
But actually, in the SDE community, I think few people focus on these parts. I mean, just define how to redefine or backward definition and combine with the joint. As in SDE community, people have less interest on these parts.
Yeah, because they don't have the need to do that.
Yeah.
I feel like I mean, if their motivation is just merely to calculate some posterior distribution, I feel this idea is kind of ponderous. I mean, of course, it's kind of a new exploration, But don't you think this is kind of like you make too much simplification and you have to you make this competition a lot of harder.
Yeah, I agree.
Yeah, I'm gonna relook at the paper who claims that they use HMC, they can do posterior inference with neural ODE itself, because neural ODE indeed works well, and Shibo has tried that, and I guess in the general application it works well as well. But if you inject SD for such a complicated things, like remember every time you just you have to sample a bunch of Gaussian noises. I'm not very sure what's their benefit.
Yeah.
Any other comments? Okay, yeah, and I think we kind of like very interested in this kind of research because they try to leverage techniques from PDEs and ODEs, SDs, those literature, but currently their work hasn't been bound to any application with physical meanings. But I think our direction will be inject some physics knowledge into the applications. But those techniques are kind of like sharing. That's why I feel it's really interesting. And also this techniques, I think, is also related to Gaussian processes. Maybe right now people are kind of like addictive to neural networks. But in many cases, like sparse observations, Gaussian processes could be a better choice. But anyway, we can just learn how how they build up such kind of bridges. This kind of like works are really interesting and novel things. We should learn from them.
Yeah, at least I think how they compute the allo to process random process. I think it sounds something maybe we can use in our work. That we use the Gaussian process. I don't know, and I think for the SD parts, like I'm saying, I prefer the alto, the common filter parts, focus on the distribution about the SD, but not the process and with such complex definition.
Yeah. If you use moment-based method, that's called sigma points method, right?
Yeah, sigma point.
Yeah, they have the ODs about the moments, the mean and the variance.
Yeah.
Yeah, we can definitely think about that. Any other question? Okay, great. So that means we don't have a seminar in this afternoon, right?
Yeah.
Okay, so I think at 12 last Friday, I asked you guys to come to the graduate lounge to talk to our faculty candidate. If you don't have any other schedules, please come too. I think they are gonna provide some pizza or drink or something. Please show up and give our candidates some welcome. Okay, so you guys know where is the graduate lounge, right? Graduate lounge.
Yes.
It's in the third floor. It's just here in the MAP building. Okay, it's at 12. You guys should come start. You should start off now. Okay, thanks, Shikai. This is a good talk. I think on Wednesday, Shibo will talk about DeepNet and the physics informed DeepNet.
Yeah, right.
Yeah, see you guys later.
Yeah, see you.